Glenn has obtained his PhD from Stanford and then spent 3 years at the IAS, Princeton, and the Canadian Theory, Institute for Theoretical Astrophysics, and now he's at Case Western Reserve University. So Glenn is a distinguished professor and the director of Center for Education and Research in Cosmology and Astrophysics at Case Western. Glenn does a lot of work on very varied subjects ranging from mini black holes, habitable planets, so the universe on large scale, CMB, and general relativity. And he will tell us about the uncooperative universe today.
Thank you, Anastasia. It's a pleasure to be here. Thanks for inviting me. So I'm going to tell you about things that I've been thinking about on and off, mostly on for way too long, maybe 15 years. And doing that with a number of people, postdocs and people who are no longer postdocs, but are colleagues at other institutions and former graduate students, and also lots of ongoing work. So for 50 years, we've been able to look up at the sky and make this incredible map. It doesn't look like much of a map, and of course that's one of the things that's most exciting about it, most mysterious about it. But everywhere we look, we see a uniform glow, nearly uniform glow, just a few degrees above absolute zero. It wasn't very long before we were able to see that it wasn't particularly exactly uniform, that in fact there was a dipole of about a part in 1,000. But of course that is, we believe, mostly due to our motion through the universe, that this is the Doppler dipole, with as well some contamination from the galaxy. So this is the galactic plane that we can see even better from this map from the 1990s, made by the Cosmic Background Explorer, where the signal of the galaxy is very strong, but all of a sudden we're able to see what we were really after, what we knew had to be there at some level, which are cosmological fluctuations at parts in 100,000. So of course, since then we've got much better. We've been able to send our satellites outside of the galaxy in order to make maps like this. Well, it'd be great if we can send them out of the galaxy. Of course, we can't. What we have to do instead is put together maps made at different wavelengths. And when the original version of this map was made, it came with this little disclaimer at the bottom that said, "Do not use for research." Of course, that didn't stop anybody. Now, the real story is that that map was actually made for research. It was also a press map because it's much nicer to show a map that has no galaxy in it, because galaxies aren't interesting to cosmologists, and you're forced to explain every time about the galaxy. If you show a map like this, you can pretend that there's no galaxy there and just talk about the cosmology. But as I said, it was really made for research. It was made in part in order to look for the large-scale topology of the universe. And what it really should have said is, if you're going to use this map for research, please be careful. Because you wouldn't be surprised if there's residual galaxy contamination in this map. So if we find a signal in of the galaxy in the map, we shouldn't be surprised. Now, of course, since then, we've made even higher resolution maps with higher signal to noise. And so I want to talk, and I'm missing lots and lots of wonderful CMB experiments, because most of what I'm going to be interested in is large-scale properties of the CMB that for which we really need most of the sky in order to talk about them. Now, when you have a map of the sky, and if you've gone to cosmology kindergarten, what you know is that you are required to expand it in spherical harmonics. And the reason for that is that our theory, our standard model for the origins of those fluctuations, inflation, tells us that the sky is statistically isotropic, and the coefficients of the spherical harmonics are independent Gaussian random variables of zero mean. So that means what we're really interested in, if we want to extract the underlying physics, is to understand the statistics of these ALMs. And our theory tells us that any pair of ALMs that aren't the same are independent, so their expectation value, the expectation value of their product is 0. But if we have the same one, then the expectation value is some number, the angular power spectrum C sub L. Okay? And notice that C sub L depends only on L. That's this fact of being statistically isotropic. So all of the interesting information, according to our theory, is contained in these C sub L's. And so what we want to do is we want to estimate the C sub L's, which approximately are the average of the ALM squareds over a given n. And if we can do that, then we've learned everything there is to know about large-scale cosmology. Now, not quite, because we can start looking for non-Gaussianities, but at leading order, that's really what we're interested in. And we've done a remarkable job. Right? You look, well, not me, because I'm a theorist, right? But I can say we, talking really about my colleagues. And what you see is enormous amounts of data in which the data beautifully fit the theory. You need 6 parameters to many, many more than 6 points. And what I'm showing you here are effectively the C sub L's as a function of L for temperature times temperature, for E-mode polarization times E-mode polarization, for the cross correlation between temperature and E-mode polarization. And you see all these wonderful bumps and wiggles of the acoustic peaks in all of them, and beautifully explained by theory line curves that go nicely through all of them with just 6 parameter fits. And they allow us to do something that I think no one would have believed 20, 30 years ago. Make charts like this that I'm not asking you to read, but to notice things like 1 plus or minus 0.0017. Who would have thought that a cosmologist would have anything like that in one of their papers? So this is an astonishing experimental accomplishment and a remarkable agreement with theory, especially for statistics that the theory tells us we should be interested in. And what I want to talk about is mostly statistics that the theory tells us not to be interested in. So the question is, but what? So what I want to talk to you about is first, alignments at low L, or in other words, the failure of statistical isotropy. I want to talk about something that often gets called the low L problem, but I'll really prefer to call it the large angle problem, or the vanishing of the 2-point correlation function. And I'll mention a little bit things like hemispheres and parity and first peaks, unless I get too caught up talking about the other stuff. And what this will lead us to is a worry that there are troubles in this fantastic cosmological paradise, and then to wonder whether we can actually tell, given that we only have one universe to measure, and we've done so much measuring of it already. So here's the first hint. And you really should realize just how bad a hint this is. So the first hint is, now here's a much earlier version of those beautiful plots from the first year of the WMAP data. And what you see here is the line is the theoretical prediction for the C sub L's of temperature. The dots are the bin values of C sub L with their experimental error bars. You see here large experimental error bars at the limiting angular resolution of the instrument. And as you go to lower and lower L's, we have very, very good experimental errors. But we get this gray band expanding, and that gray band is what we call cosmic variance, which means that up here, at L equals 400, I have 801 different A400Ms, right? Going from A400 minus 400 to A400 plus 400. And that means I get a really good estimate of C400 by averaging 801 different ALM squareds. Whereas down here at L equals 2, I only get 5. Okay, and so it's going to be very hard to get a good estimate of the underlying theory, and so I expect to get anything in this band. Now you'll notice that this point is well outside that band. Notice the quadrupole is low. And it's true that there are other points that are also well outside the bands, but there is something kind of special about the quadrupole because it represents our largest scale structures. And so this was the first thing that started to get people wondering about the large angular universe, or at least in the kind of post-Kobe era, and I'll come back and point out that even back at the Kobe era, the Kobe era, we should have been more worried than we were, more intrigued. But this lowness of the quadrupole was the first thing that was getting people worried. Now I say it was a really bad hint because the probability of getting this low quadrupole is about 10%. So it's not really a very good hint. Okay. So the low quadrupole. And this is what has become to be called the low L anomaly. And I'll come back, when I come back to it, I'll argue to you that it shouldn't be called the low L anomaly at all, and that it is much more interesting than that 10% figure suggests. But that got people really interested in all sorts of ways of looking at the theory, at the data that involve statistics that aren't really that interesting according to the theory, right? Remember, we measured the angular power spectrum, so not much else is of interest. And I'm going to focus at the beginning on something, just one. It's related to some things that were done here as well, where are they? Angular momentum dispersion axes. And I'm going to talk about it not because I think it's the most interesting, but that's completely a biased view. So I'm going to talk about alignments. If we look up in the sky and we see that things that we might have imagined would have been random, or that our theory told us should be random, and we see that they aren't, we might wonder, we might hope that they require an explanation. All right, so I want to start with the question, what directions are associated with the ELF multiple? What do I mean by the ELF multiple? I mean, when we do this expansion into spherical harmonics, only sum over m, because we know that as I make rotations of the sky, I will mix ALMs of the same L but different m's. Okay, so this is kind of a rotationally invariant subdivision of the data on the sky. Now, when we talk about the dipole distribution of something, we don't usually, in fact, talk about A11, A10, and A1 minus 1. We would usually talk about the direction of the dipole and the amplitude of the dipole. That's a perfectly natural thing because we know we can go, and we know we can go easily back and forth between these A1Ms and the amplitude of the dipole and its direction. But there are advantages to this representation of amplitude and direction because the amplitude is a scalar. If we make a rotation, then it doesn't change, and the direction of the dipole really is a vector. You know, as we make a rotation, it behaves like a vector, and so there's kind of it's natural to think about dipoles in terms of amplitudes and directions. Well, what about other multipoles? So it turns out that with other multipoles, we can think of them as products of L dipoles. Right? So because an angular momentum L object, if we take L angular momentum 1 objects, we get an angular momentum L object, then we can think of, so we can take L dipoles and multiply them to get an angular momentum L object. So in other words, instead of thinking of 2L plus 1 ALMs, I can think of L different directions and some overall magnitude. And the advantage is that these 2L plus 1, that these L vectors really are vectors. We call them multipole vectors. And that this A really is a scalar, and others under rotations, they behave in exactly the expected ways. My postdocs and I thought we were very clever when we invented this, that this was a really novel thing to do, and then someone pointed out to us that there's a nicer way to write it as L directional derivatives of 1 over r in the unit sphere, and this fellow who you may have heard of had used that before in this little known book that he wrote a little while ago. So And these are exactly the same vectors.
But he had crummy notation.
He had crummy notation, right. And we thought that no one had used this, but apparently I'm told that geometrologists use this, and there are kind of little branches of science that use this representation of the spherical, of multipoles instead of the spherical harmonic representation. Anyway, what it tells us is that, for example, the quadrupole can be thought of as an amplitude plus 2 vectors, and the octopole is an amplitude plus 3 vectors. So you can think of the quadrupole as a plane. So just take the cross products of those vectors and you get some area vector, some normal vector. And you can think of the octopole as 3 planes, just by taking those cross products. So we did that. And let me just show you where they are. And I'm going to do it this horrible old projection. And I'm doing that just because we've always done it in this projection. And I don't want to change that because then people will say, well, you're cooking, you're cooking what you're showing to us. No, we've shown essentially exactly this plot for the last decade. So this is the galactic equator, galactic North Pole, galactic South Pole, and of course you should think of this side and this side as being identified. And I want to show you where the planes of the plane of the quadrupole and the 3 planes of the octopole point. And of course, the plane of the quadrupole should have nothing to do with the plane of the octopole. They should point in completely random directions. It's almost true that the 3 planes of the octopole should be completely independent of one another. It turns out that's not quite the same what a statistically isotropic distribution would give, but it's pretty close. Okay? So in other words, those planes should be randomly oriented on the sky. And I'm going to show you both the northern hemisphere and southern hemisphere direction, because I don't know which side to put it on. But in the end, we'll focus on the southern hemisphere just because of the accident of how they sit. It's easier to look at. So here is where the plane of the quadrupole points, this kind of darkish gray dot. Now, nothing interesting about that. It's just some random place. But the 3 octopole area vectors then should point in some other random places. And here they are, 1, 2, 3, sitting right around the quadrupole vector. Okay? In fact, if we took their mean, it would sit right about there. So what we have is we have 4 planes that are supposed to be pointed randomly, and instead they're kind of nearly parallel to one another, and the 3 planes of the octopole are kind of just slightly inclined relative to the plane of the quadrupole. And it's much easier to see down here, but that's because you have to mentally move this one over to here. All right? Now, what we also did is we said, well, if there is any kind of signal like this, cosmology tells us it's not cosmological, so it probably would come from properties of the experiment. Well, what are things that the experiment knows about? Okay. Well, so this is showing that they're all grouped together. But the experiment would know about the plane of the solar system, the ecliptic. Okay, so here's the ecliptic, and notice that the quadrupole sits right nearly on the ecliptic, and these are all grouped around the ecliptic. Okay. The experiment also knows about the dipole, the direction the Earth is moving through the solar system, because that was the dominant foreground. Okay? So the dipole happens to sit right here also, this light gray dot, also very close to the ecliptic, also very close to the quadrupole. Someone said, well, they have to know about time in the experiment. They have, equations of time in there. Maybe the equinox matters as well. So here's the equinox right there. This light circle. And someone said, where's the supergalactic plane? So we put it in. I don't know why, but since we put it in the first time, we've never wanted to take it out. So what have we learned? We've learned that these 4 planes are aligned with one another, they're perpendicular to the ecliptic plane, and they are normal to the dipole, to the direction that the Earth is moving through the universe. Now, the area vectors tell about the orientations of the multipole planes, but they don't include all the information, because I can take these planes and rotate them, right, about their common axis, especially when we have this planar structure where they're all where they're all basically parallel to one another. So let me just show you a picture of the quadrupole and octupole together, added together. And what you see is these 1, 2, 3 extreme. There are 6 extrema here. 1, 2, 3, 4, 5, 6. 3 of them south of the ecliptic, 3 of them north of the ecliptic. Notice how the ecliptic kind of very carefully separates these 3 from these 3. That'll be kind of strange. It's hard to tell, but this is the strongest one. This is the next strongest one. These 2 are tied, and these are very weak. We'll come back to that. And then this is the plane of the quadrupole, which is very nearly perpendicular to the plane of the ecliptic, and passes nearly right through the centers of these extrema. So what we have here is basically these 6 extrema defining a band perpendicular to the ecliptic plane, quite well aligned with each other. So notice that I'm actually showing you something called the SMICA map, which means that this is coming from Planck, not WMAP. So that gives you a hint that this didn't go away when Planck flew. Everyone thought, well, this is some issue with WMAP. It is not. It's on the sky. Unless they share some common systematic. So maybe it's a foreground, maybe it's, we'll see. One really interesting thing, this DQC means it's Doppler quadrupole corrected. So we knew that we had to subtract the Doppler dipole, but people have kind of done estimates and shown that you didn't really need to worry about the Doppler quadrupole. The quadrupole contribution of the quadrupole, it's too small. It turns out it's true that for looking at the amplitude of the quadrupole, it's very small. But for looking at the kind of phase relationships between the ALMs, or in other words, how these planes are oriented, it matters. And strangely, it turns out that when you correct for the Doppler quadrupole, you find that you move the average of the you move the quadrupole from area vector from here to here, and that turns out to make it align much more closely with the average of the octupole vectors here at the start, which is completely random if it's random. Okay, so are we just reading tea leaves? How unlikely is this? Well, so the chance that the quadrupole and octupole planes would be this aligned in lambda CDM is between 1 in 1,000 and a few in 1,000. Given that you have that the quadrupole and octupole planes are this aligned, the chances that they would be this perpendicular to the ecliptic are somewhere between a couple in 1,000 and a couple in 100. And this range depends on exactly which version of these maps you use. Okay, because there's all sorts of different ways of combining the different waveband maps and to take out the foregrounds. Once you've noticed that they're this aligned and perpendicular ecliptic, the chance that they would then be pointing at the dipole as well as they do is a few percent. Once you've noticed that they're aligned and perpendicular to the ecliptic and pointing at the dipole, the chance that they would be then turned in this nice way so that the ecliptic carefully separates the extreme in the north from the extreme in the south is again a few percent. Now, just since all of these are conditional probabilities, I could multiply them all together, right, and get some number less than 10 to the minus 7. But I'm not even sure which of these is real. Are any of them cosmology? It's hard to imagine the ecliptic's cosmology. So I'm tempted to multiply them together, but I'm also reluctant to. So could this be cosmology? That would be a nice physical model, but that this is cosmological. But how do you get correlation with the dipole? Because after all, the dipole has to do with the Earth's or the sun's movement in the galaxy and the galaxy's movement in the local group. Surely the universe does not know that the sun is going around the Milky Way. And it's quite difficult to come up with a model in which the quadrupole, the angular power in the quadrupole is so much less than the angular power in the octupole. Okay, so the most reasonable thing would be that this was systematics. But and when we just had one experiment seeing this, WMAP, that was a reasonable thing to expect. But Planck and WMAP are very different experiments, and so no one has figured out a way to get this in either of them, never mind both of them. I told you that we shouldn't trust this map, that we should expect to see correlations with the galaxy. Now, of course, we're not seeing correlations with the galaxy. We're seeing correlations with other things, but maybe the galaxy is accidentally structured in such a way as to correlate with these other things. Well, the problem is that what we're seeing here are y22s and y33s. In other words, if we choose our axis well, the fact that we have these nice strong planes tells us that we can choose a z-axis perpendicular to those planes, and we'll find that the quadrupole and octopole are mostly y2 plus and minus 2 and y3 plus and minus 3. That's called planarity. And it is not the right multipole structure for the galaxy, for looking at the galaxy. Certainly not with the z-axis that we have to choose, which is through the dipole, not through the center of the galaxy. And so it seems to have the wrong multipole structure to be galactic contamination, which is not surprising since we don't see galactic contamination. Now, you can imagine that it's other foregrounds. Like, you can imagine that you could change a patch of sky. And there are many papers that say, oh, just change this patch of sky and you'll get quadrupole and octopole and there'll be a line. The problem is if you change a patch of sky, typically you get YL zeros, not YLLs. And it's also hard when you change a patch of sky to explain why you get 5 times more octopole than quadrupole. And many of the explanations try to do this as a perturbation series in some small quantity that we forgot. Okay? But then you have to understand why that, typically those perturbation series say, okay, the quadrupole is first order in the perturbation, and then the octopole is second order in the perturbation, and instead we have to have the octopole be first order and the quadrupole be second order. So you have to explain why you have more octopole than quadrupole. Okay. Then, if it's a foreground, why is it perpendicular to the ecliptic? People have looked for, maybe there's something, some dust clouds, sitting above the or below the plane of the solar system. But so far, it's we haven't seen it. How do you hide this foreground from detection? It would have to have a temperature very similar to the CMB. So the alignments are there. They're persistent. They're individually interesting, which I mean, they're at the level of 10 to the minus, few 10 to the minus 3, and collectively very significant. It's hard to explain or establish priority. In other words, which one of those do I believe, and which one do I not believe? Or do I believe them all? And so the question of how to make progress. So I'll come back to that in a bit. But because first I want to talk about what I'm going to call the uncorrelation. I'm going to come back to this low quadrupole, which we've kind of forgotten. We've been talking about the quadrupole, but not really the fact that it's low. And suggest that really we should look up here at this other axis that talks about, that's in degrees, not in multipole moments, that says that what we're really talking about is large angles. And in the days before COBE, the people doing COBE being, at the time, proposing COBE at the time being astronomers, they didn't know initially that they were supposed to be interested in angular power spectra. They thought they were supposed to be interested in two-point correlation functions, so in angular correlation functions. And so they would have probably published the two-point angular correlation function of the microwave background, and that is to take pairs of points separated by some angle, and average multiply them, and then average over all such points separated by that angle, and you get the angular correlation function. But by the time the experiment was actually being done, theorists had become very clear that what was interesting was the angular power spectrum, and so that's what people focused on. And of course, they contain the same information. Well, just because they contain the same information, differently organized, doesn't mean one is less interested in the other, right? We Fourier transform things, we transform things all the time, because sometimes you see the signals more clearly in one version, one side of the transform than the other. So the COBE folks did eventually, in their 4th year paper, publish the two-point angular correlation function, and this is what it looks like. Now you can't tell whether this is interesting because they don't tell you what they expected. But what you will notice is that it's 0, above about 60 degrees, except for this anti-correlation at large angles, very large angles, near 180 degrees. So here's a W map. Well, here's a plot that we made using W map data from their third year. And what you'll notice is here is the expected two-point angular correlation function. This blue band is the cosmic variance. And one of the reasons why it's so much easier to think about angular power spectra is because in the theory, the different CLs are uncorrelated. They're statistically independent. That's not true of the two-point angular correlation function. So it's not like I can choose arbitrarily any value in this blue band over here and any value in this blue band over here. You know, the choices are correlated. So I'm just showing you the 1 sigma range of possible values of the angular correlation function, but you shouldn't think that I can just put any curve I want through that blue band. Okay. But then I'm showing you here the Q, V, and W maps, the two-point angular correlation functions extracted from those maps outside the galaxy. So outside the part of the sky that we're supposed to believe. We're supposed to doubt. And you'll notice that they all come down here, and then they are effectively 0 over this very wide range of angles from about 60 degrees up to 170 degrees. And that's also true of that synthetic sky, this ILC, right, that I showed you over the same range. This dashed line follows the data, which is not surprising, right? If you have a map where the data doesn't have correlations, you would not want your synthetic map to have those correlations. However, if you include the part of the sky that includes the galaxy, then you get this solid black line, and maybe it's not surprising that it turns out to have correlations on these scales, and we'll see in a minute where they come from. Now, interestingly, if you take the values of the CLs ultimately reported by WMAP, they follow this full sky ILC and not the partial sky ILC. In other words, they have the large angle correlations that are there in the sky that includes the galaxy, not in the one that excludes the galaxy. So we go from a map in which the data has no large angle correlations to reported results which have large angle correlations. Now, what's important to realize is what's strange about this result is not that it's not sitting along the dashed lines. It's not even how different it is from the dashed lines. Okay? What's strange about this is that it's 0. How strange? Well, the WMAP folks realized that it was strange. They wrote down the statistic called S1/2. And consistently over the years, that statistic, when calculated over cut skies, had ended up being there, possible by chance in Lambda CDM at the level of about 3 to 5 parts per 10,000. So 3 to 5 times out of every 10,000 realizations of Lambda CDM will give you this little angular correlation. Well, where does the correlation in the full sky map come from? It all comes from pairs of points. So the red and green curves are, the red curve is what you get if you look at the part of the sky outside the galaxy. And the blue curve is what you get if you let at least one of the points lie inside the galaxy. So apparently all of the correlation we see on the full sky map is due to pairs of points, at least one of which is in the galaxy. So maybe there's some accidental galaxy correlation, contamination. Did this change in Planck? No, absolutely the same. All right, well that's very strange. And there's 2 ways this could be happening. It could be a 1 to 10 in 10,000 chance, that this is happening over the full sky, that this is really a full sky property of the universe. Or it's also possible that what's actually a conspiracy between 2 only mildly unlikely things. One is that the 2-point correlation function is only 5% unlikely, but most of the correlation is hidden by the galaxy. That's possible. The thing is, if this is physics, in other words, if the fact that we see over the part of the sky that we actually trust, this incredibly unlikely absence of correlations, then it really tells us something very important. Because you can't just fix it in the easy ways that we would think of fixing it. So the first thing you would think of doing is saying, well, I'll just change my inflationary potential so as to give me different CLs, like the CLs I see, so that I'll then get a low 2-point correlation function. And the problem is it doesn't work that way. It doesn't work that way because of cosmic variance. So if I change my predictions for the CL to be exactly what I measure, okay, and then I will predict that the expected value of the 2-point correlation function is what I measure, and so I will expect no large angle correlations. But the cosmic variance will then cause that to be completely spoiled when I don't go to a realization. And you'll find that there would only be a 3% chance of recovering so little correlation in a particular realization. But almost all the time when you do that, it would look nothing like the current data. That's because when we look here, what it would predict, the easiest way to get no correlation at large angles is to have all the CLs be 0. But they're not. The way we're getting very little large angle correlation is by a conspiracy of L equals 2, 3, 4, 5 to cancel what's going on from 6 to 20. So somehow they are adding up, the CLs are adding up so that when you construct C of theta, which is the sum over CLs of Legendre polynomials of cos theta, you get, even though the individual CLs are not necessarily that small, the angular correlation function is very close to 0. So that says, what does that mean? Well, it could just be a statistical fluke. It's the easiest explanation. But if it's physics, then it suggests that the YLMs are the wrong basis to preserve Gaussianity. So either we have to give up Gaussianity, or we have to give up that the spherical harmonics are the right basis. So we could replace that basis. For example, we could imagine that there's cosmic topology, and others there are short, just loops around the universe, and then you would replace the Fourier basis by the eigenmode basis, and so then that would correlate the different YLMs, the different ALMs, and can give you a small angular correlation function and perhaps alignments. Or we can imagine that what's really going on is that there's some sort of compact support basis. In other words, that large distances aren't actually correlated in the way that the Fourier basis suggests they are. Let me talk about one more, very quickly. Low Northern Variance. So, as has been noticed long ago, if you look at this map, the south is different than the north. And I'm pointing over here, this is the ecliptic south, this is the ecliptic north. The ecliptic south is much busier than the ecliptic north. And in fact, if you go out and look at it, okay, the ecliptic south, the variance of the ecliptic south, what is the units here? Micro k squared. The variance of the ecliptic south is right in the center of the distribution, right in the median of the distribution, I guess like in the peak of the distribution of what you expect from lambda CDM. And the ecliptic north has a very small variance. 10% smaller than the expected variance, and that happens by accident about once in 1,000. And there's several other things. There's something called the Parity Anomaly, which points out that odd multipoles seem to almost always be bigger than even multipoles. And it turns out that these other points that are anomalous are only anomalous in the part of the sky near the ecliptic poles, not in the part of the sky near the ecliptic plane. And so the real question is, with so many anomalies and not knowing which ones or if any are physical, what do we do? And so I think there are 3 ways to make progress. The first is we should write down a fundamental physical model and make testable predictions. The second is, if we can't do that, we should at least make reasonable phenomenological extrapolations and test them. And the third is we should see are there ways of actually testing the fluke hypothesis? The idea that this is just a statistical fluke, that's a hypothesis. So in other words, Lambda CDM will now make different predictions. Once you know that the temperature sky is an unusual realization of your statistics, that will make different predictions for other observations, and we should go check those. So here is a list of new models that I know of that do more than just kind of explain one anomaly, that it kind of explain at least two anomalies. Okay, that's the list. I don't know them, not so far. It would be nice to have some, and we have some ideas, and maybe we'll even have a paper about one of them sometime soon, but I don't know of any. So if you have one, let's talk about it. I'm happy to put it on this list. So let's focus instead on these other two possibilities, phenomenological extrapolations and testing the fluke hypothesis. So the philosophy here is that assume an anomaly is physical and guess what that implies for other observables. And the fluke hypothesis is to assume that this is just lambda CDM, it's just statistics, and see how the measured anomalies affect predictions for other observables. And they seem to always go hand in hand. So for example, let's take, because I think this is the first one that we're actually going to make progress on, this low northern variance. The fact that the northern temperature sky seems to have lower variance than it should, and the south is normal. And people have called this, instead of, they've also called it the dipole asymmetry, they've called it the hemispherical asymmetry. They're just different ways of describing the same thing. So here's a phenomenological guess, which is that if you have low variance in temperature over a large region of the sky, that will imply low variance in the field that was responsible for those temperature fluctuations, and which is also responsible for the polarization fluctuations, at least the E mode, which is the largest part of the polarization, in that same region of the sky. And so what does lambda CDM say? It says it doesn't make any difference. Well, almost no difference. It makes a little bit of difference. It lowers the variance a little bit. This is now the polarization variance in the north and in the south, and you can see that the dashed line, which is the conditional prediction, that says what does lambda CDM predict, knowing what we know about the temperature in the north, and it changes a little bit, but not very much, and it changes just about equally in the north and south, and that's because of how that's because of how polarization and temperature are correlated. So a change, you're not going to be able to notice this change.
Sorry, I don't understand the difference in the dash and the solid.
Oh, the solid line is what lambda CDM predicted before you made any measurements. Having made a measurement of the temperature map, we can now say, okay, what does lambda CDM predict for the E mode polarization? And it's slightly different because T and E are correlated. So the piece of E that is determined by T, okay, is now fixed. And it has low variance, so that lowers the variance of the E mode polarization a little bit, but not very much, because they're not that tightly correlated in lambda CDM. Okay, so you get a slight shift, and it was kind of surprising to us before we thought about it much that you got to say the same shift in north and south, but that's because the ALMEs contribute with different L weightings to E. The Gaussian variable that determines the temperature contributes with a different weighting to the E mode polarization than it does to the temperature. And that different weighting means that they don't add up. Things that were just in the north in temperature end up split between north and south. All right. So you see a small reduction in the polarization variance about equal in north and south. But the gas would say that we expect a larger reduction in the variance in the north, like a 10% reduction. And so here is what if you look along this axis, if you took the predicted variance of around 12.6 and reduced it by 10%, that would get you somewhere over here. It would be extremely unlikely. It's a p-value too small for us to actually compute with the I think 10,000 with the 100,000 realizations that we did. Now it turns out, fortunately, you don't even need the entire northern sky. You can just get, say, the piece of it that you could see from Chile, and still, if you go from 12.6 down to 11 point something, you're way off the charts, and you have a really tiny chance of that happening by accident. So that says that if you go and measure the variance of the E-mode polarization, which is essentially all the polarization in the northern sky, and you find something significantly below the expected value, like by what you might guess it might be, then that would be real argument against this being a lambda CDM fluke. On the other hand, if you find exactly, kind of exactly what you expect in lambda CDM, which is what lambda CDM predicts, then that would suggest that the T variance was just a fluke. So we can do this. We can do this for all sorts of other observables, and ask the question, what can we learn? And so there's all sorts of observables that we haven't measured yet, like cross correlations between T and lensing and the various things that we can imagine doing such things with. What about this absence of two-point angular correlation? Well, so remember we saw no correlation essentially in temperature above 60 degrees. We might imagine that we will see the same thing in E. And we know from 2008 that there will be changes to other correlation functions, but it turns out that they're not that big. So this is the difference between what the lambda CDM prediction this is for the cross correlation of temperature and Q-mode polarization. You can think of it as E-mode polarization. The temperature, this is the lambda CDM prediction, and this is the constrained lambda CDM prediction. In other words, the prediction you get having already looked at the temperature data. And so they change, but not enormously. Maybe enough for us to be able to see. So if we found something that if we found something that was right in this peak, it doesn't tell us very much because unfortunately these peaks are nearly the same. So it's actually a little bit difficult for us to now distinguish between these, okay, using just this. But if we were thinking about with our phenomenological hats on, we would say, okay, so let me go out, here is what lambda CDM predicts for the QQ and UU modes of polarization, which contribute to E-mode polarization. And lambda CDM says that they still have lots of correlation or anti-correlation, but if my idea that there's really physics underlying this absence of correlation above 60 degrees, then I would expect that the Q and U will again be uncorrelated above 60 degrees. And so if I go out and measure this and find that the QQ and UU correlations are very small, that would be evidence against lambda CDM and in favor of a physical explanation, the need for a physical explanation for the absence of correlation above 60 degrees. Another phenomenological guess would be that the absence of angular correlation is not because we live at a special place at the center of the universe, right? That if 2 points at a particular angular separation effectively on the last scattering surface are uncorrelated, is because pairs of points that distance apart are uncorrelated. And that allows us to, instead of just looking at pairs of points on the last scattering surface, to also look at pairs of points in which one's out there and one's closer in, or they're both on the interior of the last scattering surface. And so we can look at cross correlations not just of temperature, but of temperature in E-mode, and E-mode and E-mode, and temperature and lensing, and large-scale structure, etc. And lambda CDM tends to predict at best mild changes in these cross correlations. So, in summary, the sky appears not to be a typical realization of Gaussian random statistically isotropic. The temperature multipoles are aligned with one another and are with the ecliptic dipole. The temperature sky lacks large angled correlations. There are noticeable hemispherical and asymmetries or differences, etc., etc. I'd say there's no good model so far for this. Not systematics, not foregrounds, not cosmology. And so while the cosmic orchestra may be playing the lambda CDM symphony, someone gave the bass and the tuba the wrong score, and they're trying very hard to hush this up. There's no good theory for any of this yet. but we may be able to test explanations anyway. Thank you.
Thanks for very nice talk and other questions.
If these anomalies are aligned with the ecliptic, why isn't that the simplest explanation?
Well, that would be so the alignment of the quadrupole and octopole with the ecliptic. If that is the right thing to focus on, that would say that there's something going on in the solar system, or the near neighborhood of the solar system, that explains this, right? And people have looked. People have gone out and looked for emission from slightly warmer than the CMB, and just not found anything. Okay? You might have thought it was initially we thought, well, could this be zodiacal light or something like that? No, zodiacal light is exactly in the wrong place. This is I don't know why I think the solar system is like this, but if this is the solar system, it's up above the solar system, perpendicular, not in the plane of the solar system. So it doesn't seem to be zodiacal light. We have no evidence of some gas thing going across like that. Yes.
What's the ecliptic longitude of this great circle?
So I forget the answer to that question, but it's a great circle basically perpendicular to the equinox. So the equinox is effectively at the
solstices.
Yeah.
So there are claims, if not very good statistics, of the dipole in the fine structure constant. How do you know where the pole of that is compared to your various poles?
I thought that one didn't align very well, but I may be wrong. At least when someone came and gave a talk about it, and I asked him to tell me where it was, he pointed to a different part of the sky than where the CME dipole was. So.
What might be learned from large volume galaxy surveys?
Right.
So you get away from this single surface, and now you have more modes.
So I think the biggest difficulty there are two difficulties with galaxy surveys. First of all, if we're thinking in L space, it takes a lot of galaxies to get the quadrupole to these low L multipoles to high enough precision that because we're talking about fluctuations whose amplitude are like 10 to the -5. So these are fluctuations that haven't had an opportunity to grow, right? So they're very low amplitude fluctuations. So they're not very good at low L modes. The second thing is, and you can see that in the fact that I think at this point the 2-point correlation function in any object survey hasn't been measured beyond about 10 degrees. I think is the largest. So it's a long way from 10 degrees kind of to 60 degrees. So in principle, there are things you can learn. In practice, it's hard. And in particular, I'm told that getting the systematics down to the point where you really trust that your galaxy survey over there and your galaxy survey over there are the same. That you have no systematic effects in the 2-point correlation function across 90 degrees or 60 degrees is really tough. But that's not some. I can tell you about the statistics of the numbers, but not you need like 10 to the 9, 10 to the 10 galaxies. We're getting there. That's certainly possible. But I'm told the systematics are a bigger issue.
Okay, will clear up.
Could be.
I just wanted to say, nice to see Paul Henry's.
It never gets shown.
Never gets. Yeah, he was my boss at Bell Labs, and Bob Wilson's boss. So, yeah.
And not the
said,
person.
Yeah, I saw the first anisotropy, and nobody ever remembers that. It was his PhD thesis.
Oh, really? Yeah. I don't know why we don't show that, because it was, of course, an important landmark measure.
Flying around the U-2s with heat-warmers.
So I have a question. Are
Yes.
higher multiples aligned and planar?
so when people first started looking at this, they, you know, when we first started looking, we were looking up to multiples of like 50, 100, and there are all sorts of strange things that go on. You know, there are other multiples that are much too planar, and there are other multiples that are much too isotropic. So there was an Imperial College group with Jaume Geisha that was very interested and used a slightly different language, and they kept being interested in, and it's kind of about very early on I decided that there was too much chance. The higher you go in L, the more multiples there are, or the more ALMs, the more multiple vectors. So the easier it is to see sheep in the clouds, you know, or to be reading tea leaves. So I just said, okay, look, there is strange stuff going on here, and you know, if 2, 3, and 8, and 13, and 27, and 48 are all weird, and you know, we're just going to get into arguments about a posteriori versus a priori statistics, which aren't going to teach us anything because it's all a posteriori. How can I tell you whether, you know, we have to go out and go beyond that and start looking at, you know, doing what I think what we're trying to do is say, okay, it's there on the sky, and we can, it may or may not be, it may be a fluke, it may not be a fluke. How do we figure that out? But yes, there are other weird things at higher up.
If there are no more questions, let's.
I just want to show one slide, which is that in June there will be 2 conferences in Cleveland at CASE. One is a 50th anniversary celebration of the Standard Model, and if you are we would love to have everyone, but in particular if you're a graduate student or postdoc, we have money to help support your visit. And then PASCOS will immediately follow that from the 4th to the 8th. So we welcome all of them.
Thank you.
Still recording, that's good.